Here's lesson 3, multiplication of a vector by a scalar. So make sure you've gone to the link in the description, you've got your lesson book ready, and we'll fill it out together. So let's get going. Part 1, scalar multiplication. So over here I have a diagram of a bunch of vectors that are scalar multiples of each other. In this section we'll be multiplying a vector, we'll call it vector A, by a number k to produce a new vector k times vector A. The number k used for multiplication is called a scalar and can be any real number. Multiplying a vector by different values of a scalar k, which can be any real number, can affect the magnitude and the direction of the vector. If we look at this diagram over here, all these vectors have different magnitudes because they've been multiplied by different scalars. And the directions of the first 4 are all the same, but the directions of the next 3 are all in the exact opposite direction. And we'll talk about why that happens and when that happens as we move forward here. And then another statement it says here, when two vectors are parallel, these vectors are described as being collinear. They are described this way because they can be translated to be on the same straight line. Scalar multiples of vectors we'd say are collinear. So what I have here are two vectors that are scalar multiples of each other. Let's call this one vector A. This one is in the opposite direction, but it looks like it has about twice the magnitude. So I'll call this -2 times vector A. Right, multiplying a vector by a negative is going to reverse its direction. It's going to be going in the opposite direction. And multiplying it by -2 not only reverses its direction, but it's going to double its magnitude. And these two vectors, because they're scalar multiples of each other, we'd say they're collinear, which means if I were to translate them on top of each other, they would fall on the exact same line. So those two vectors are collinear, as are all vectors that are scalar multiples of each other. Let's start by looking at a list of rules. The first thing we want to do is distinguish the difference between what happens if we multiply vector A by a scalar that's positive compared to if we multiply vector A by a scalar that's negative. So let's start here. Rule 1. If k is greater than 0, so if the scalar is positive, then k multiplied by vector A is in the exact same direction as vector A, so direction is not changed if the scalar is positive. And the magnitude is equal to k multiplied by whatever the magnitude of vector A was. And now let's break this down into two parts. If the k value is between 0 and 1, then vector A is shortened. The magnitude, for example, of half times vector A is equal to half of the magnitude of what vector A was. And if k is greater than 1, then that actually makes vector A longer, right? So the magnitude of, for example, 2 times vector A is equal to 2 times the magnitude of what vector A was. So let me show you what I'm talking about with the diagram below here. So this is vector A. If I were to multiply vector A by a scalar between 0 and 1, let's say 0.5, it's going to make the vector shorter. It's going to have half the magnitude of the magnitude of vector A, and it's going to be in the same direction. So this would be 0.5 times vector A right here. Half the magnitude of vector A in the same direction as vector A. And this one is longer, so the k value must be bigger than 1. And it looks like it's about twice as long, so I could say this is 2 times vector A. It's in the exact same direction with twice its magnitude. Now let's look at if your k value is negative. So if you multiply vector A by a scalar that's negative, then k times vector A is in the opposite direction as vector A, with a magnitude that's equal to the absolute value of k times the magnitude of vector A. So let me talk about that. If the k value is between -1 and 0, it shortens it, and it changes it to the opposite direction. Right? Because it's negative, it changes it to the opposite direction, and because it's between -1 and 0, it's going to make it shorter. So for example, the magnitude of -1/2 vector A, so if we multiplied A by -1/2 and we found its magnitude, that would be equal to 1/2 of the magnitude of vector A. The negative just changes it to the opposite direction, but its magnitude is half that of vector A. And if k is less than -1, then vector A is actually lengthened and changed to the opposite direction. So let's say we had negative 2 times the vector of A. That magnitude would be equal to double the magnitude of vector A. So let me give you a demonstration down here with this diagram as well. So here's vector A again. If I multiplied vector A by, let's say, negative a half, it's going to make its magnitude half that of what it was before, and it's going to change it to the opposite direction. So I'd have to change this vector to be going in the opposite direction as vector A, and make its magnitude half of what it was before. So this would be negative 0.5 vector A. And this one, it looks like it's about twice the magnitude. So if I wanted to multiply vector A by negative 2, it would have twice the magnitude but be in the opposite direction. So let me change its direction to being in the opposite way again. So now it's going in the opposite direction as vector A, but it has about twice the magnitude, so I'd say this is negative 2 vector A. Rules 3 and 4 here are fairly self-explanatory. If we multiply a vector by 0, then what we get is the 0 vector. We don't just get 0, we call it the 0 vector. So you write 0 with a vector symbol above. And the distributive property for vector multiplication is if we do a scalar times a sum of vectors, what we can do is use the distributive property and do k times vector u plus k times vector v. So the distributive property holds true when doing scalar multiplication with vectors. Example 1. An airplane is heading due north at 1,000 kilometers an hour. The airplane's velocity is represented by this vector right here, vector v. Draw the vectors negative vector v, a half vector v, and negative a half vector v, and give an interpretation for each. So this one, the airplane is going due north 1,000 kilometers an hour. So the length of this vector represents its magnitude 1,000 kilometers an hour, and the arrow represents the direction of north. So let's draw negative vector v. So when we multiply a vector by negative 1, it's not going to change its magnitude, but it's going to make it go in the exact opposite direction. So I can copy and paste this vector to keep its magnitude exactly the same. So you'll have to use a ruler to actually go ahead and make sure you measure and make the vectors the same length. But I need to reverse its direction. So this would be an example of negative vector v. Exact same magnitude, opposite direction. And let me just color code this. Let's make this one red. So there's negative v. Same magnitude as v, opposite direction. Now let's do a half vector v. So a half vector v, since the scalar is positive, it's going to be in the exact same direction, but it's going to be half the original magnitude of vector v. That looks like it's about half the magnitude, and it's in the exact same direction as v, so I will call this a half vector v. And lastly, let's do negative a half vector v. So it's going to have the exact same magnitude as this one, but it's going to be in the opposite direction of this one. Right? The negative scalar is going to reverse its direction. So let me reverse its direction. And let's color code this one green. We'll call this one negative a half vector v. Negative a half vector v. So notice a positive scalar keeps it in the same direction, a negative scalar makes it go in the opposite direction. And now it says to also give an interpretation for each of these. So remember the magnitude of this one was 1,000 and it was going north. So the magnitude of negative v is the same magnitude, so it's still 1,000 kilometers an hour, but it's going in the opposite direction. So we'd say due south instead of due north at 1,000 kilometers an hour. Same magnitude, opposite direction. This one, same direction, but half the magnitude. So if the magnitude of this one was 1,000 kilometers an hour, well, a half of that would be 500 kilometers an hour. So in this case, this vector is heading due north at 500 kilometers an hour. Same direction, half the magnitude. This one is opposite direction and half the magnitude. So we would say this vector is heading due south, right, opposite direction, at 500 kilometers an hour, half the magnitude of the original vector. Example 2, consider vector u with magnitude 100 kilometers an hour at a quadrant bearing of north 40 degrees east. So this question, it gave us the magnitude and the direction of the vector. And what it wants us to do is draw each of the following vectors that are scalar multiplications of vector u. So first thing we want to do is we want to draw the vector 3 times vector u. So it's going to have 3 times the magnitude of vector u, but be in the same direction because the scalar is positive. So vector u had a magnitude of 100 kilometers an hour, so 3 times vector u is going to have a magnitude of 3 times that, 300 kilometers an hour, and it's going to be in the exact same direction. So let's keep the direction the same, and our drawing needs to be 3 times as long. So the length of this one is 3 centimeters, so the length of 3 times vector u should be 9 centimeters. So let me go ahead and draw that. And I'm going to put the arrow at the end of it to indicate that it's going in the exact same direction as vector u was. So this is vector 3 times u, and its magnitude is 3 times 100 kilometers an hour, so its magnitude is 300 kilometers an hour, going in the exact same direction. So if I want to describe this vector, I would say the velocity is 300 kilometers an hour, 300 kilometers per hour, going in the exact same direction. So it's still going at a quadrant bearing of north 40 degrees towards east, exact same direction. Part B is 0.5 times vector u. So it's going to be going in the same direction as vector u because the scalar is positive, but its magnitude is going to be half that of vector u. So instead of 100 kilometers an hour, it's going to be 50 kilometers an hour. So let's keep our diagram accurate by measuring off half of vector u. So vector u is 3 centimeters, so a half times vector u should be about 1.5 centimeters. So let me draw that. And the arrow is going in the same direction as vector u, right? It's going in the same direction, but it's half the length. So this is a half vector u. Its magnitude, I should label it instead of 100 kilometers an hour. The magnitude of this vector is 50 kilometers an hour. And let's describe this in a little sentence off to the side here. So this vector is 50 kilometers an hour. That's its magnitude. And it's in the same direction as vector u. So it's still going at a quadrant bearing of north 40 degrees east. Part C, this is the first time the scalar has been negative. We want to draw negative 2 times vector u. So it's going to have double the magnitude of vector u and be in the opposite direction of vector u, right? When the scalar is negative, changes it to the opposite direction. So let's figure out what double the magnitude of this vector would be, right? The length of this is 3 centimeters, double the magnitude is 6 centimeters. So I need to draw a vector that is 6 centimeters long and in the opposite direction. So I'm going to draw it, instead of going in this direction, I'm going to draw it going the opposite way. I'm going to draw it going this way. And it's 6 centimeters long, twice the magnitude. So I'm going to put the arrow at the end of this, indicating that it's going in the opposite direction that vector u is going in. So this is negative 2 vector u. And its magnitude is twice as big as this one, so instead of 100 kilometers an hour, it is now 200 kilometers an hour in the opposite direction. And if I'm going to describe the direction using a quadrant bearing, I should get this angle here, and opposite angles are equal, so I know that this is 40 degrees. So I could say that this vector is 200 kilometers an hour at a quadrant bearing of south 40 degrees west. Here's some properties for scalar multiplication of vectors. So I've already talked to you about distributive property. Distributive property holds true for scalar multiplication of vectors, but also the associative property tells us that the order of multiplication doesn't matter, right? So if we're multiplying vector v by 2 scalars, it doesn't matter whether we do a times b times vector v, or b times vector v first and then multiply that by a, or a times vector v first and multiply that by b. It doesn't matter. And also the identity property, if we multiply a vector by 1, you get the original vector. 1 times vector v just equals vector v. So for this example, we need to make sure you understand how vector addition works when we're working with algebraic vectors, because the example we're going to do next, over here, we're going to be adding and subtracting some vectors together. So you just need to know how you can collect like vectors together. So I've defined 3 vectors here for you, x, y, and z. Let's just get an expression that's equivalent to each of these in terms of I, j, and k. And these letters will become more significant to you once we learn about algebraic vectors and unit vectors in future units. But for now, let's just get an expression for each of these in terms of I, j, and k. So vector x plus vector y. We'll replace vector x with what it says it's equal to. And now replace vector y with what it says it's equal to. So now we have an expression where it's a sum and difference of a bunch of vectors. So I've got 3 times vector I minus 4 times vector j, and so on. Now, when we're adding and subtracting vectors, we can treat them like terms. So 3 times vector I doesn't have any like vectors, so I can just leave that one. -4 vector j plus 1 vector j is -3 vector j. And vector k minus 5 vector k is -4 vector k. Let's try part B. So let's start by replacing vector x with what it says it's equal to. And then I replaced vector y with what it says it's equal to, and now I can use my distributive property to know I have to subtract both of those vectors, and then I'll collect my like vectors. So I have no like vectors with vector I, but I have -4 vector j minus 1 vector j, that's -5 vector j, and 1 vector k plus 5 vector k, that's 6 vector k. Part C, let me start by replacing vector x, y, and z with the vectors that tells me they are equal to. And now I can use my distributive property. And then lastly, I can collect any like vectors I have. 3 vector I minus 3 vector I, that's gone. -4 vector j minus 2 vector j, that's -6 vector j, minus 3 vector j, that's -9 vector j. And 1 vector k, 10 vector k, 12 vector k, that's 23 vector k. Okay, this is probably the most important example we're going to do in this lesson. In this example, it tells us we have a trapezoid ABCD, where BC and AD are parallel. So these are parallel, that's important. And it says that this one is 3 times the length of that one. It also says let AB equal U, let BC equal V. Express AB, BD, and CD as linear combinations of U and V. Okay, let's start with vector AD. So let's come up with an expression for vector AD written in terms of vector U and vector V. So vector, and also I want you to notice the arrows on these, right? It says that vector AB is vector U, and it says that BC is vector V. That's why the arrow's over here. It goes from B to Z. If I want to describe this vector in terms of U and V, it tells us right here that this vector here is equal to 3 times the magnitude of this vector. So I could describe this vector right here as, since it's in the exact same direction as vector B, but with 3 times its magnitude, I could say that this one is equal to 3 times vector V. So this one here is 3 vector V. The next one, vector BD, so now I'm looking for this vector. I want to come up with an expression for this vector. I'm actually going to have to do this one as a sum of 2 vectors. Remember, when adding 2 vectors, you place them tip to tail, and then the resultant vector goes from the tail of the first vector to the tip of the second vector. So this vector, if I were to add this vector and this vector, what I would get would be that red vector BD, right? Because vector BA and AD are placed tip to tail. The sum of those 2 vectors would be from the tail of B to the tip of D. When adding vectors, it always goes from the tail of the first vector to the tip of the second vector. But I want to write this in terms of U and V, right? So if I want an expression for this one, vector BA, well, that's the opposite of AB. So BA, I could call that as -U. Same magnitude as U, but in the opposite direction. And then I need to add to that this vector here, which we figured out in the previous question is 3V. So I've expressed vector BD, this one right here, as a sum of -U and 3V. Now let's do vector CD. We want this vector right here. So I'm actually going to express this vector as a sum of 3 different vectors, right? We can add as many vectors as we want together. As long as they're placed tip to tail, I know the sum of them goes from the tail of the first vector to the tip of the last vector. So for example, to get from here to here, I could add this vector, and this vector, and this vector, right? The sum of those 3 vectors would be the vector that goes from the tail of the first vector to the tip of the last vector. And now I just have to come up with an expression for those 3 in terms of U and V. Well, this vector here, this first one, is in the opposite direction of V, but with the same magnitude, so I could call this -V. This vector is the opposite direction of U, but with the same magnitude, so -U. And this one we figured out was 3V. and then I can collect the negative vector v with the 3 vector v, right? That's why we did the previous example, to show you that we're allowed to do that. So we get negative u plus 2 times vector v. The last thing I want to show you is how to create a unit vector. And unit vectors are going to be important when we want to define a direction of something without changing its magnitude. We can multiply it by a unit vector. But in the meantime, let's just figure out what a unit vector is. So let's read this together. It is sometimes useful to multiply a non-zero vector x by a scalar 1 over the magnitude of x. When we multiply vector x by 1 over its magnitude, we get a vector that has length 1. This is a vector of length 1, and it's called a unit vector. It goes in the exact same direction as vector x, but we've manipulated its magnitude to become a magnitude of 1. That's why we call it a unit vector. So this vector x, if it has a magnitude of 3, if I were to multiply this vector by a third, what I would get is a vector in the exact same direction as x, but with a length of 1, right? If this was a magnitude of 3, then this one becomes a magnitude that's a third times the magnitude of x, which was a third times 3, which becomes 1. Right? Let's say something had a magnitude of 5. If I wanted that to become a length of 1, I'd multiply it by 1 over 5. 5 times 1 over 5 is 1. Right? So if you multiply something by 1 over its magnitude, it makes the magnitude become 1. So the last example is example 5. Given the magnitude of vector u is 4 and the magnitude of vector v is 5, and the angle between u and v is 120 degrees, determine a unit vector in the same direction as u plus v. So the first thing I should do is, so we want a unit vector in the same. Last example, example 5. Given that the magnitude of u is 4, the magnitude of v is 5, and the angle between them is 120. So when we define an angle between two vectors, and this says angel, when we have an angle between two vectors, it means when they're tail to tail. So if it says the angle between vectors is 120, that means if they were tail to tail, the angle between them is 120. Determine a unit vector in the same direction as u plus v. That means find a vector that goes in the direction of u plus v, but has a length of 1. So let's start by figuring out what vector u plus v looks like. So I'd have to place vector u and v tip to tail. So let me reposition vector v so its tail is at the tip of vector u. So here's vector v, right? I didn't change its directions or its magnitude. I just changed its position on the screen. Vector u plus v would go from the tail of vector u to the tip of vector v when they are placed tip to tail. So let me draw that vector. So there's vector u plus v I drew in red. So we want to come up with a vector that's in the exact same direction as this, but has a length of 1. So what I'm going to have to do is multiply vector u plus v by 1 over its magnitude. So we're going to have to figure out the magnitude of this vector. Well, what do we know? In this diagram, we know the magnitude of vector v is 5, and we know the magnitude of vector u is 4. And I could figure out the angle between them. If you remember angle properties, right? Co-interior angles equal 180. So I know that this angle and this angle have to equal 180, so therefore this angle has to be 60 degrees. And then since I know two sides in a contained angle, I could use cosine law to figure out the length of the side opposite from the contained angle. So cosine law would tell us that the magnitude of this side squared equals the magnitude of this side squared plus the magnitude of this side squared minus 2 times the magnitude of the product of those two sides times cosine of the contained angle. And I could simplify this. And cos of 60, if you remember your special triangles, cos of 60 is a half. So we've got 41 minus 20, that's 21. Let's move the squared over. So the magnitude of u plus v equals the square root of 21. So I know the length of this side is root 21. So our final answer when we're describing a vector that's in that direction with a length of 1, well, I take vector u plus v, which has a magnitude of root 21, and I multiply it by 1 over that magnitude to make its magnitude become 1 while keeping its direction in the same direction as u plus v. So there's my unit vector. So that's it. Make sure you try the practice questions.